So we're going to use the three criteria for continuity of a function at a point to help us ensure that this function we have presented here, a piecewise-defined function, is continuous on the entire interval from -infinity to infinity, or for all real numbers. So the task is, what value of c would make the function f of x continuous on the interval -infinity to infinity? So the three criteria that we need to attend to are, first of all, that the limit as x approaches a of a function, our function f of x, exists. Now, in this particular case, if I look at the portion of the function that is defined for x less than 2, what I see is a linear function, 3x plus a constant, that is continuous on its domain. It's basically a polynomial, and polynomials are continuous on their domain, and there are no domain restrictions for that particular function. If I look at the portion of the function that is designated for x greater than or equal to 2, I again see 2 times a constant, which is a constant. I see minus constant times x squared. So this is basically a constant minus some multiple of x squared, which is also a polynomial. So this portion of our function f of x is continuous on its domain. So it is continuous for all x greater than or equal to 2. So then my two pieces are both continuous. The only question left to remain is this function continuous at 2? Because it will be continuous everywhere else at x equals 2. So when I consider whether the limit of the function exists, I'm focusing on a particular value of a. I'm going to focus on what happens precisely at 2. Then we're going to have to consider whether f of 2 exists. And then the third criteria is to consider whether the limit as x approaches 2 of f of x actually equals f of 2. If we can satisfy all three of those for some value c, then we will have met the criteria for making this function continuous on the entire real number line. So let's go ahead and start by trying to create a condition under which this limit as x approaches 2 of our function actually exists. So let's first look at the limit as x approaches 2 from the left. From the left means that we're looking at values of x that are smaller than 2. So we're looking at that part of our piecewise defined function. So we're looking at 3x plus c. And what does that limit actually evaluate to? Well, it evaluates to 3 times 2 plus c, or 6 plus c. Now considering what happens to our function as we take the limit as x approaches 2 from above, this time we're looking at values of x that are greater than 2. So we would be focusing on that portion of our piecewise defined function. So we would have 2c minus cx squared. And taking that limit, we would have 2c minus c times 2 squared. Simplifying here, we would have 2c minus 4c, which simplifies to be negative 2c. Now recall that for the limit as x approaches 2 to exist, that the limit as x approaches 2 from the left of f of x must equal the limit as x approaches 2 from the right of f of x. So what that means for this function is that 6c, that's my limit from the left, must equal negative 2c. And now I have a rather simple algebra equation to solve. I'll subtract c from both sides of the equation, so I get 6 equals negative 3c. And then I will go ahead and divide by negative 3, giving me that c should equal negative 2. So in letting c equal negative 2, we have guaranteed that the limit as x approaches 2 of f of x exists, and that limit is equal to, it could either be, we could either think of it as 6 plus negative 2, which is 4, from the left, and we could look here, and we'd have negative 2 times negative 2, which is also 4. So the limit as x approaches 2 of f of x exists and is actually equal to 4. So we've taken care of the first criteria to ensure that this function is continuous everywhere, especially at x equals 2. Now the second criteria is that f of 2 is defined. Well, we discovered that we would need to let c equal negative 2, so let's rewrite our function using that information. So we would have 2 times negative 2 minus negative 2x squared for x greater than or equal to 2. And we'd have 3x plus negative 2 for x less than 2. So is f of 2 defined? It is. The condition here of x greater than or equal to 2 would indicate that this would be the portion of our piecewise function that we would use to find the value of f equals 2. So finding the value of f equals f of 2, I'm sorry, not f equals 2, but f of 2. F of 2 would be 2 times negative 2. That minus a negative 2, I'm going to turn that into plus 2 times 2 squared, which is equal to negative 4, plus 2 times 2 squared is 8. So f of 2 is defined, and f of 2 actually equals 4. Now, our third criteria. To ensure continuity is to ensure that the limit as x approaches 2 of f of x equals f of 2. Well, we saw in the first criteria that the limit as x approaches 2 of f of x is equal to 4, provided that we chose c to equal -2. Okay, so the left-hand part of this equality is 4. And then in part 2, we saw that based on that choice of c equals -2, that f of 2 would also equal 4, which is a true statement. So this means that with the selection of c equal to -2, we have ensured that this function, f of x, is continuous on the interval from -∞ to infinity. I hope this helps.